Welcome to our module on large language models, or LLMs. In the following video, we'll establish a conceptual understanding of what LLMs are, how they're trained, and how they function. This foundational knowledge is essential for anyone looking to leverage AI, particularly for business applications. Our aim is to provide clarity on these core concepts without delving into deep technical jargon, enabling you to better identify opportunities and contribute to AI projects. This diagram illustrates the central position of the LLM within the AI systems we'll be discussing. As you can see, the LLM is the core engine that interacts with instructions, knowledge, and actions. In this specific module, our primary focus will be on understanding the LLM itself. We'll explore its fundamental nature before moving on to how it's guided by instructions, enhanced by external knowledge, and empowered to perform actions in later modules. Many of us are already familiar with AI chatbots like ChatGPT, Claude, or Gemini. These chat interfaces, which function as AI assistants, are built upon large language models. While they are powerful, their internal workings are often opaque to the user. To effectively design and build more sophisticated AI agents and AI workers, it's essential to first understand this core engine, the LLM. Grasping these fundamentals is the first step toward creating more advanced AI systems. So, what exactly is a large language model, or LLM? At its core, an LLM is a type of artificial intelligence specifically designed to understand and generate text that closely resembles human language. It functions as a complex prediction engine built upon what's known as an artificial neural network, and it's trained on vast quantities of text data. Through this extensive training process, the LLM learns to identify patterns and relationships between text characters. This enables it to generate text that is often remarkably coherent and relevant based on the patterns it has learned. The engine powering an LLM is an artificial neural network, or ANN. You can think of the ANN as the complex computational core of the LLM. While the concept of an ANN is inspired by the interconnected network of neurons in the human brain, it's important to understand that it's fundamentally a mathematical system designed for pattern recognition in data. The diagram here provides a simplified visual representation of such a network. In an artificial neural network, information flows through layers of processing units, which we call nodes. These nodes, represented by the circles in the diagram, are connected by links. The links are represented by the lines between the nodes. Each of these link connections has an adjustable weight, or strength. These weights are critical as they determine the influence one node has on another. During the LLM's training, these weights are systematically adjusted, which is how the network learns to perform its tasks. The process of training an ANN involves feeding it massive amounts of data. Over time, this training refines and adjusts the weights or strengths of the connections between nodes. As the diagram illustrates, with strongly connected nodes and strong weights, some connections become more influential than others. This allows the ANN to learn and recognize extremely complex patterns within the vast data set it's exposed to, while the underlying operations involve complex mathematics, such as multiplying large matrices of numbers. The core concept is that training shapes these weights to capture and represent patterns. The key concept to take away here is that this process of adjusting weights through training enables an LLM and its underlying artificial neural network to perform pattern recognition at a massive scale. The result of this is that an AI chatbot can generate human-like text that often appears more sophisticated than the underlying mathematical operations might initially suggest. This emergent capability for coherent text generation stems directly from this large-scale pattern recognition. The training of an LLM typically occurs in stages. The first major stage illustrated here is pre-training. This is an initial large-scale training phase where a foundation model is built. During pre-training, the model develops its core language understanding by processing vast amounts of raw text data. As shown, this training data can come from diverse sources like the internet, Wikipedia, books, and social media archives. This extensive exposure allows the model to learn grammar, facts, different writing styles, and some basic reasoning abilities. The primary goal of this pre-training phase is for the foundational model to learn broad language patterns and various writing styles. This process can take months, during which the AI effectively reads the input data. As it processes this data, it's continuously adjusting the weights and strengths of the connections within its neural network, particularly between related and non-related characters or tokens. Over time, the model becomes increasingly proficient at predicting missing or subsequent characters and words in a sequence. It's important to note that pre-training is a very expensive endeavor in terms of compute power, time, and financial resources, which is why relatively few organizations build these foundational models from the ground up. So, after this intensive pre-training phase is complete, how does the resulting foundational model actually work when we interact with it? This diagram provides a simplified overview of that operational flow, showing an input, the foundational model mechanism, and an output. The process begins with user input, which is essentially a sequence of characters. Humans typically interpret these sequences as words forming questions or statements, like the capital of France is, as shown in step 1. This input is then fed into the model mechanism, as indicated in step 2. The model, using the learned patterns it acquired during its extensive pre-training, then predicts what sequence of characters or tokens is most likely to follow. Following its prediction, the model generates an output, as seen in step 3. This output is another sequence of text, in this case, Paris, which humans typically understand as the answer to the input. However, it's crucial to understand a key point about foundational LLMs. Out of the box, they don't understand dialogue, context, or user intent in the way humans do. The model is essentially completing patterns based on the vast amount of text it was trained on. It makes this prediction based only on the text provided at that specific moment in that particular interaction, without inherent memory or deeper contextual awareness. To better understand how LLMs process text, we need to discuss tokens. LLMs don't see text as humans do, word by word or character by character. Instead, they break text down into these tokens, which are the basic units they process. As you can see from the examples, a token can be a whole word like intelligence, a part of a word like art, and official for artificial, or even punctuation. The phrase artificial intelligence doesn't is shown here as being broken into 5 tokens. Most LLMs have a vocabulary of tens of thousands of unique tokens learned during pre-training. This system allows for efficient compression of language into machine-readable token IDs, which are numerical representations, as shown on the right. The LLM then operates on these numerical IDs. At their fundamental level, LLMs operate as next token prediction engines. When given an input sequence, such as the capital of France is, the model doesn't know the answer directly. Instead, it calculates a probability distribution across its entire vocabulary for what the very next token is most likely to be. For instance, the token for Paris might have a 92% probability, Lyon a 2%, located a 1%, and so on, with thousands of other tokens having much lower probabilities. The LLM then typically selects the token with the highest probability, or samples from the most probable tokens, to generate its output. This process is repeated token by token to form a complete response. Because foundational LLMs are essentially sophisticated pattern predictors trained on vast, often unfiltered internet data, they inherently have significant limitations, especially when considering their use in reliable business applications. As this slide outlines, their next likely text prediction mechanism can lead to several problems. They might produce incorrect or nonsensical information, often referred to as hallucinations, as humorously depicted by the model outputting located on the moon. They can also reflect biases present in their training data, leading to biased or offensive content. Furthermore, without additional refinement, they may not follow instructions effectively or could generate responses with an inconsistent or undesirable tone or style. Given these limitations of foundational models, there is a clear need for a process to guide them towards more desirable behaviors. We need them to be more helpful, honest, harmless, and generally aligned with user intent. This process of refining the model to meet these criteria is broadly referred to as alignment. The solution to the limitations of foundational models is a second training phase known as alignment fine-tuning. As the diagram illustrates, this involves providing human feedback to the foundational model. A common and effective method for this is reinforcement learning from human feedback, or RLHF. Unlike the initial pre-training, which uses massive raw data sets, alignment fine-tuning typically employs smaller, high-quality data sets and incorporates direct human guidance to teach the LLM the desired behaviors and to steer it away from undesirable ones. The data used in alignment fine-tuning, particularly with RLHF, often consists of good example conversations written by humans or human rankings of different AI-generated responses to the same prompt, indicating which are better or worse. The diagram shows examples of this, such as rating responses based on how well they follow instructions or whether they avoid making things up. The overall goal of this human feedback process is to make the LLM more helpful by ensuring it follows instructions and provides useful information, more honest by training it to avoid fabrications and admit its limitations, and more harmless by guiding it to avoid biased, toxic, or unsafe content. The result of this alignment fine-tuning process is what we call an aligned model. This aligned LLM, as depicted here, is significantly safer and more reliable for real-world interactions compared to its purely pre-trained foundational counterpart. It's better at following instructions, providing truthful information, and avoiding harmful outputs. These aligned models are the ones that typically power the AI chatbots and assistants we use today. This slide illustrates the practical difference an aligned LLM makes. Given the user input using bullets, list 3 food cities in Italy, an aligned model is more likely to produce a helpful and accurate output, like the more of example listing Bologna, Naples, and Rome, with relevant details. In contrast, a less aligned or purely foundational model might produce an unhelpful or incorrect output, like the less of example, which is not a list and includes non-Italian cities. This demonstrates that aligned LLMs are crucial as they form the foundation for effective conversational AI. We'll explore conversational AI in more detail in our next module. To summarize this module on LLM fundamentals, we've seen that LLMs learn language patterns from vast amounts of data during their initial pre-training. Their core function is to operate by predicting the likely next sequence of text. However, these pre-trained foundational LLMs have inherent limitations, such as potential inaccuracy, bias, and a lack of nuanced control. To address this, alignment tuning, often using techniques like reinforcement learning from human feedback, employs human guidance to make these LLMs helpful, honest, and harmless. It is these aligned LLMs that then form the critical foundation for effective conversational AI systems.